Hello and welcome to lecture 2 of Motion in a Straight Line, and we're going to be defining position, time, and displacement in this lecture. So you're texting to your friend Sam and you ask, "Where are you?" And Sam says, 12. Well, you probably very politely text back with, "Sam, that's not a very useful answer. Can you clarify, please?" Or something like that. You might begin asking clarifying questions like, 12 watts? From where? In what direction? What is wrong with you? So a useful answer would have included a reference point, like Sydney, say, a direction, like south on Highway 4, and a distance with units. And those are the minimum you always need to provide whenever you're giving a position. In textbooks, a position is often defined as the location of an object, but I don't think that's a very good definition. You can ask me, "Where's the ruler?" and I can point at my desk and say, "Right there." And I've told you the location, but I haven't told you the position. If I tell you instead 20 centimeters left of my coffee mug, then that's a position. A position is what you get once you've assigned numbers to a location. And we won't normally give reference points like Sydney. Our usual reference point is an origin of a coordinate system. So what we mean by that, this is a technical term. We don't mean where something starts. We mean the place where the axes cross, the place where all the coordinates are 0. In one dimension, we only have one axis, but there's still an origin. It's the place where the position on that axis is 0. And on one side, positions are positive, and on the other side of the origin, positions are negative. So that sets up a sign convention, and that sign convention now carries through for all other quantities that have a direction, like velocities and so on. And just note that it's a choice which way you say is positive. It's also a choice where you set your origin. Now, I'm going to say over and over that there's no such direction as negative. Left, right, up, down, east, west, those are all directions. Negative and positive are not directions. Once you've defined axes, you can now start talking about positive and negative. However, as soon as we're into 2 dimensions, negative or positive are no longer sufficient to define directions. And so it's best just not to get in the habit of ever describing directions as positive or negative unless you're already talking about one axis. So just to illustrate what I mean, here's a one-dimensional motion example. We have this machine that moves back and forth on rails, so it only moves in one dimension. It has some resting position, and let's say it goes left more often than right. So we might define the resting position as the origin. And because it goes left more often, maybe it's convenient to define left as positive. And so now if I say x is plus 1.53 meters, it's unambiguous that that means 1.53 meters to the left of the resting position. So positive is sufficient to define a direction here. But now let's think about sometimes when it isn't, right? That was a one-dimensional example. But if we're in a 2-dimensional example, then it's not sufficient. So let's say we're field biologists and we are logging the motion of a roadrunner. Maybe we might choose the nest as its origin. It's presumably near the middle of its territory. And let's say I say that the roadrunner is at plus 550 meters. Well, that's ambiguous. What do I mean? That could be 550 meters east of the nest, maybe, or north of the nest, or even up. So plus and minus is ambiguous here. And in general, in 2 dimensions, you never want to specify directions that way. We'll get there. You need vectors, and we haven't done that yet. Now let's talk briefly about time. Time is just as important as position when we're describing motion. Just think about this hair. Let's say this hair moves 10 meters in 2 seconds. Well, it's behaving quite differently from this tortoise that goes the same 10 meters in 0.1 seconds. So time matters. And a lot of the same ideas apply. We need to define a reference time, just like an origin for our time axis. And negative times are going to refer to times before the reference time. Now, I often hear students say there's no such thing as negative time. But presumably, if positive times are after the reference time, then all we mean by negative times are times before the reference time. Motion is all about change, so let's take a moment to carefully define change. And we'll work with something maybe more familiar, a bank balance. So let's say on Monday your bank balance is $1,100 and on Tuesday it's $1,400. I think you'll agree with me that the change is $300. Now, go back on Wednesday and it's 1,000. Now, you might say that the change is 400, but I'm going to say that if your numbers representing change don't tell you whether the change is an increase or a decrease, that's not so useful. So this, we should say, is a change of negative $400. Now, both of these are consistent with defining changes by a final minus initial. So we'll say a change is going to be, in this case, a delta B for bank balance. And I've said BM and BT, right? So I'll say B final minus B initial, right? So this is how we always define it. And so, for example, you see that the delta B on Tuesday from Monday is B Tuesday minus B Monday, and that gives you the $300. And similarly, your change in bank balance on Wednesday from Tuesday would be B Wednesday minus B Tuesday. And so notice that these labels final and initial, we allow to float. We redefine them as needed. Changes in position are so important that we give them a special name. We call them displacement. And so it's defined just like any other change. We say the change in position is a final position minus an initial position. I just want to highlight this symbol here is called delta. And it means change in. And so this whole thing here, delta x, refers to one quantity. This is not delta times x or anything like that. That's one quantity. Now, one other thing to just point out is that displacement is very different, as we'll see in an example, from distance. And usually what gets stated is that a displacement is a distance with a direction. But in fact, we're going to see that when things are changing direction in their motion, there's an even bigger difference between displacement and distance than that. Let's do an extended example to see how some of these ideas work. So here we're putting a ball. We're putting uphill, and we're starting 6 meters below the hole, and the ball rolls 2 meters past the hole, and then 1 meter back towards it. And the first thing I'm going to do is define axes. And remember, we can define them any way we want. I'm going to choose to put my origin at the hole, and I'm going to set the positive direction for x down the hill. Now, we're not going to need a y-axis, but I'm going to put it there so that we see where the origin is. All right, so there's the y-axis, there's the x-axis. So I've just defined down the hill as my positive direction. And now I'm going to start giving things names, because we're going to have to talk about positions and times and so on, and it's hard to talk about things if you haven't given them names. So I'm going to call the instant that we putt the ball t0, and I'm going to define that as 0, the time that is 0. And now look at x0. I've defined my origin here, and we're 6 meters in the direction I've called positive from it, so that's plus 6 meters. All right, so now this is going to be t1, and we're told that's 5 seconds. x1, it is 2 meters from the hole, and it's uphill, and so that's negative 2 meters. And then this is going to be t2. It's 3 seconds later, so 8 seconds. And x2 then is negative 1 meter. And now I'm going to calculate some displacements. So for the time period from t0 to t1, I'm going to call that displacement delta x 1, 0. You might say 1, 0, why not 0, 1? Well, I'm using 1, 0 just to remind myself that I have to take x1, which is my final, minus x0, which is my initial. x1 is negative 2 meters minus plus 6 meters is x1, or x0, and so there's negative 8 meters. There we go. And just look at that and think about it. It's negative. Well, that displacement is up the hill, and that's our negative direction. So now I'll do the same thing for the time period from t1 to t2. So I'll say delta x21 is x2 minus x1, which is negative 1 meter minus negative 2 meters, or plus 1 meter, and that again makes sense because the ball rolled downhill during that time period, and that's our positive direction. Just want to close off by illustrating the difference, a big difference, between displacement and distance. So here's everything we've done previously, and there are those two displacements from 0 to 1 and from 1 to 2, and I've added in the displacement all the way from start to finish. Right, from t equals 0 or to t2, 8 seconds. And it's negative 7 meters. Overall, the ball has wound up 7 meters up the hill from where it started. But the distance traveled is not 7 meters. You know, if you walk 3 kilometers to school and then walk home, no one's going to say that you've walked no distance. The distance traveled is going to be, well, first it went 8 meters up the hill. Then it came 1 meter back down the hill. The total distance traveled is 9 meters. So not only does the distance not have a direction associated with it, here the negative is telling us about direction, it's not even the same size as the displacement, because we calculate it in a very different way.